Welcome to the video for C5.3.1, where we're going to look at reversible reactions. So to start with, pause the video and try and explain which of the following processes can be reversed and think about what that tells us. Okay, so hopefully you've got the idea that when we've taken eggs and we've cooked them, so we've fried them in this case, we can't reverse them. So if I take my egg and I fry it and then I decide, actually, I'm not in the mood for a fried egg, I wish I'd boiled it, I can't turn it back into a raw egg and start again. So that can't be reversed. If I take turn milk into yogurt, and then I decide, you know what, I don't want yogurt, I want a cup of tea, so I need to turn it back into milk, we can't turn that back. So here's a picture of something dissolving in water. So if I've dissolved something in water and I want to get pure water back, what I can do is I can evaporate the water and condense it again, and I can get pure water. So that is reversible. And then in this one, I've got water turning into steam. So I can turn steam back into water. So if you've ever held anything cold above a kettle as it's boiling, you get little droplets of water condensing. So that's reversible. So hopefully you remember from year 9 that if something can't be easily reversed, then it's a chemical change. And if it can be easily reversed, it's a physical change. So in a physical change, there's no new substance. So no new substances are made, so it can be easily reversed. Whereas in a chemical change, we've got at least one new substance being formed, and therefore it's usually difficult to reverse. But if you've noticed the title of the lesson, which is Reversible Reactions, you'll have realised that there's some chemical reactions which we can reverse, and that's what we're going to learn about today. So learning objectives for today, you need to be able to describe some reactions as reversible, give some examples, and then describe the conditions under which dynamic equilibrium occurs. So a reversible reaction, so just pause the video and copy this down. So a reversible reaction is a chemical reaction that can go in both directions. So normally we have the reactants can turn into the products, but sometimes those products can be turned back in to reactants. Now, we don't want to write it out twice, so we could do 2 arrows like this to show that the reactants turn into the products, but the products turn into reactants. But we don't draw it like this. Instead, we have this special arrow for reversible reactions where we draw half an arrow going forwards and half an arrow go backwards. So this sign indicates a reversible reaction. So we have the reactants turn into the products, but the products can also turn into reactants. So a classic example of this, which you'll learn about more in year 11, is the Haber process. So the Haber process is making this chemical called ammonia, which is really important for fertilizers, as we'll learn in year 11. So you turn nitrogen and hydrogen into ammonia, but as you make the ammonia, some of those ammonia molecules react back with each other to give nitrogen and hydrogen. So there's 2 reactions happening at once. The nitrogen and hydrogen are turning into ammonia, but then the ammonia is breaking down, it's decomposing to give nitrogen and hydrogen. So what we find with reversible reactions is that when we've got a closed system, so a closed system means that no reactants or products can be added or removed. So it's a sealed closed system where nothing can get in or out. So when we have a reversible reaction in a closed system, what we find is that eventually we get to a state of equilibrium where the rate of the forward reaction and the backward reaction is equal. And because the forward reaction and the backward reaction are going at equal rates, the concentration of the reactants and products doesn't change. But the reactions are still happening. So even though the concentrations of the reactants and products aren't changing, some reactants are still turning into products and some products are still turning back into reactants. But it's just because that's happening at the same rate that the amounts of the concentrations of the reactants and products are not changing. And this is a very important principle in chemistry. So we need to copy this whole slide basically down. So we need to know the equilibrium is when the rates of the forward reaction and the backward reaction are equal, and that means the concentration of the reactants and products isn't changing. We also need to know that only occurs when we've got a closed system, because if we've got an open system, then one or more of the reactants or products can escape, and that disturbs the equilibrium, which we'll look at in the next lesson. Now, sometimes it's called dynamic equilibrium because that gives this idea that the forward and backward reactions are still happening. So if you've not copied that down yet, pause the video. Right, there's a good, if you follow that link there or type that link into your search engine, you'll see there's a good video that uses a model to show equilibrium and reversible reactions. Okay, second video that's worth watching, if you go to TED, there's a video on if molecules were people, and that explains reversible reactions as well. And third video, there's a practical where you can see copper sulfate turning into anhydrous copper sulfate and then that being reversed if you follow that link there. So there's a diagram of the experiment that you'd see. So you end up with, you have hydrated copper sulfate, which is a nice blue colour. You heat it with a Bunsen burner, the water evaporates, and you end up with anhydrous copper sulfate. And then if you add the water back again, you get the nice blue crystals. Okay, so here's a typical exam question. So ammonia is made from nitrogen and hydrogen. This reaction is reversible. Explain what that means. So pause the video and try and answer this question. And then unpause when you're ready to check your answer. Okay, so hopefully you've written something about the reactions going both ways, or this idea that the reactants react to make products, but the products react to make the reactants. Sometimes in exam mark schemes, we have this allow. So it's allowing the idea that it goes back to the start or its original state. But that's an allow. So don't write that in an exam. You want to write this bit here because that's the ideal answer. Okay, so second exam question here. So it's giving you a reversible reaction between carbon dioxide and hydrogen to make methane and water in a sealed container. So that sealed container is our closed system. This reversible reaction forms a dynamic equilibrium. What is meant by that term? And it says refer to both the concentration and the rate of the reaction in your answer. So that will be 1 mark and that will be the second mark. Okay, so pause the video and have a go at this and then unpause when you're ready to check your answer. Okay, so for the first mark, so concentration, we need to say the concentration of reactants and products doesn't change. And for the rate, we need to say the rate of the forward reaction equals the rate of the backward reaction. So for the same question here, we're going to look at how many marks is this answer worth. So in this sample answer, they've written the rate of the forward reaction equals the rate of the backward reaction. So pause the video and write down how many marks you think that is worth. Okay, so this is our mark scheme. So use that mark scheme to work out how many marks that's worth. Okay, so hopefully you've come up with 1 because it's got the rate of the forward reaction equals the rate of the backward reaction, which is this one here. So we've got that mark, but we haven't mentioned the concentration, which is there. Okay, second sample answer for us to have a go at has the concentration of all the chemicals don't change and the rate of reaction in both directions is the same. Okay, so for that one, we've got both marks awarded because the first mark is the rate of the forward reaction equals the rate of the backward reaction, and that's here where it said the rate of reaction in both directions is the same. So that's our first mark, and then it says concentration of reactants and products does not change. So the concentration of all the chemicals don't change. Okay, that's the end of the lesson. Thank you for listening. See you next time.